Reflection. Reflection is simply the bouncing of light rays off of a surface, and you probably already knew that because reflection is part of your everyday experience. Not all surfaces reflect light. Some do and some don't. Some surfaces absorb most or all of the light that strikes them, and some reflect all or part of that light, and the way in which a surface reflects light determines how it looks to us. For example, the color, for one thing. If you have a red ball sitting here, the reason you perceive that as red is because the light shining on it, say the sunlight is shining on it, this sunlight that we call white light really consists of light of all different colors. When that light lands on the ball, all of the light is absorbed except for the red light. The light that is the particular wavelength or particular frequency that corresponds to red is reflected off, and that enters your eye when you look at it. The red light comes into your eye and you perceive the ball as red. All the other colors are being absorbed. And the same is true for any other color. If you see something that's blue, the reason it appears blue is because it's reflecting blue light into your eye. Now, if you're watching this video, you're actually looking at a computer screen, not a ball right there. And the reason this circle on your screen appears red is because it is emitting red light. That's not really reflection. So just pretend like this is an actual ball in the real world and light is striking it. The reason a red ball appears red is because it reflects red light. Now, whenever you have light coming in and striking something, the incoming light rays are called incident rays. So incident is just a synonym for incoming. So there's incident light rays, and I'll draw these coming in basically parallel. The sun is very, very distant, and in this context you can think of it as a point source, and the incoming rays are basically parallel. But when they strike the surface may appear smooth, but most surfaces are really rough on a microscopic scale. In other words, if you were to zoom in and magnify that surface, it wouldn't just be straight. It would consist of a lot of little jagged sections, maybe some flat pieces, but it's not at all smooth. And so the incoming light rays, the different rays striking different parts of the surface, are hitting different facets here at different angles. So some of these light rays are going to get reflected in some directions, some are going to get reflected in others. And the result here is what we call diffuse reflection. The light scatters. If the surface really is smooth, though, on a microscopic scale, like a polished piece of silver or smooth glass, then the incoming rays, which are all basically parallel, get reflected in a parallel fashion. And if you're watching this, if your eye is over here, this is your eye from the side. Okay, so that's your eyeball right there. And these would be eyelashes on top and on the bottom. So if you're looking and you're looking this way, you see the light enter your eye. You see a bright spot right down here where the light is striking it. This is called specular reflection. And we've seen a lot of this in everyday life as well. Here's a graphic that shows 5 steel balls in this room with some colored walls, and the ball on the right is highly polished and very smooth. You could see this, if this were real, you could see the one on the left for the same reason you could see anything, because light striking it reflects off and enters your eye. But notice there's no bright spots on this one. There aren't any specular highlights, as we would call them, like you see over on these on the right. The ones on the right are literally more smooth on a microscopic scale. This one on the left is more rough, and when the light hits it, it scatters. This one has a more mirror-like finish. And you see other things reflected. You see the red and blue and green walls and ceiling reflected in there because of the specular reflection, as well as the bright spot from the light shining on it, what we would call a specular highlight. And sunlight reflecting off of the water is another example of specular reflection that we're all familiar with. When we're studying reflection, it's often helpful to consider a single ray of light coming in and striking a surface, and we can represent that ray with a straight line. It comes in and strikes the surface at a certain angle, and the angle that it strikes at is called the angle of incidence. Now it's important to remember that we always measure these angles relative to the normal. So take the point at which the light ray strikes and draw a line perpendicular to the surface at that point. And remember, the word normal simply means perpendicular. So that's the surface normal at that point. The angle here that the ray of light makes with the normal, that is what we call the angle of incidence. So the incoming ray is the incident ray, and the angle that it makes with the surface normal is called the incident angle, or the angle of incidence. And then the ray hits the surface and it bounces off. And this angle here is called the angle of reflection. The angle of reflection. And this ray bouncing off is, of course, called the reflected ray. Now, the law of reflection is very, very simple and intuitive. It simply says that the angle of incidence equals the angle of reflection. So this angle, the incoming angle measured relative to the normal, equals the reflected angle measured relative to the normal. And that fits with our everyday experience with ordinary objects. If you have a wall and you throw a tennis ball at the wall, it's going to bounce off. And the incoming angle, you should understand, and you should have experienced things like this, approximately equals the reflected angle. Some spin on the ball might change it a little bit, but the general idea is always the case. If you throw a tennis ball straight at the wall, it's going to bounce straight back. And if you throw it at a very shallow angle, it's going to Now we're going to talk about refraction, and here's a graphic showing some refraction. This is a glass of water with a straw in it, and you can see the bend, or the apparent bend, in the straw. The straw is in this orientation, but when you look through the surface of the water, you see it in another orientation. It appears to be bent. And you also see down here through the glass, because of the curvature of the glass and the water, you see some magnification. The straw is fatter in this region than it is up here. So, and the bending and the change in size, both of those are due to the refraction of the light. When you look at this straw, your line of sight goes through the water to see the straw there, or through the glass to see the straw there. And in either case, that light is coming from that part of the straw through the water or the glass and into your eye. And when light travels from one material to another, it often bends like that. And the bending of light when it travels from one material to another is called the refraction. The bending, or the changing in direction, that's refraction. And I'll explain to you why refraction occurs. Here's a diagram that's very common, just showing basic refraction. This is supposed to represent a piece of glass. The green rectangle there is a piece of glass. So this is glass, and out here is air. In other words, all around here is air, and then inside this is a solid piece of glass. And glass is transparent, light can go through it, and we have a light ray striking the glass. And when it enters the glass, it bends, it changes direction. So if we were to draw a normal right here perpendicular to the surface, we get two angles, and the angles are always measured relative to the normal. This angle is the angle of incidence, and we commonly represent it with the letter I. And this angle down here is the angle of refraction. Commonly represented by the letter R. Now, why does the light bend when it goes into the glass? You can understand that if you understand that light changes speed. Now, the speed of light is a constant, and that's one of the fundamental constants of the universe. And we've learned that the speed of light, c, is 3 times 10 to the 8th meters per second. Specifically, that is the speed of light in a vacuum. And by vacuum, of course, I mean empty space, going through nothing, not like a vacuum cleaner. That's the speed of light in empty space in a vacuum. In other materials, light typically slows down. So when it goes into the glass, it slows down, and that slowing causes it to bend. Now I'll try to explain why light bends when it slows down as it enters the glass. When you're drawing a diagram, there's a lot of ways you could imagine drawing a light wave. You could just draw a ray of light, a beam of light, like I've been drawing. That's like a beam of light coming out of a laser. You could draw an individual little particle traveling along, and we've called individual particles of light photons. So you could think of it as a photon. Sometimes people draw a little sine wave with an arrow on it like that, and the curve there, the little up and down sine wave, indicates that light is a wave. You could also draw it as wave fronts advancing, kind of like we did when we drew diagrams for the Doppler effect, and we imagined these sound waves advancing along in one direction, but we thought about the little wave fronts and the distance between them and those sorts of things. So you could represent a light wave in a diagram in a variety of ways, and in some cases it makes sense to use one representation, in other cases it makes sense to use another. When we're talking about refraction, if you want to measure these angles, the angle of incidence right there, or the angle of refraction right here, it makes sense to think of the light as a straight beam of light, these little rays of light. But if you want to understand why refraction occurs, why the light slows down when it enters the glass, that's most easily seen if you draw the wave fronts. So imagine this light ray as consisting of wave fronts. This would be kind of like waves approaching the beach. If you have the beach here and you have these waves coming in, you don't picture this as a ray coming in. You picture it as the wave fronts, the individual long wave fronts approaching the beach, roughly parallel to each other. So picture these light rays coming in toward the glass as wave fronts. Now, when the light enters the glass, it slows down, so you can see that this end of this wave front has entered the glass first, so it slows down a little bit. These out here are still moving at the speed of light until they're in the glass. They're moving at the speed of light in air. Once they're in the glass, they slow down, so they don't move as far each time now. And the light ray has bent. So you can picture something moving along, and then this side of it getting snagged here, and this side continuing to move at the same speed. So it ends up bending as it comes into the light, as it comes into the glass. Now this ray of light comes on out the other side and bends again, and the opposite happens. When these wave fronts emerge from the glass, inside the glass they're still traveling relatively slowly, but when they come out they pick up speed, so they move a little bit farther because they're moving at higher speed, and the light ray ends up bending again. Okay, not a perfect diagram, but I think you get the idea. The change in speed causes one end of that wave front to slow down when it enters the glass, causing it to bend, and it causes one end of the wave front to speed up before the other as it emerges from the glass, causing it to bend back. So that's why the refraction occurs. Refraction is the bending of light when it goes from one material to another, and it happens because of the change in speed. Light goes at different speeds in different materials, and the change in speed from one material to another causes the bending, causes the refraction.